Hi, everybody. We are Group 8, and today we are going to be discussing Chapter 13, which is the first section on linear optimization. My name's Lottie.
I'm Hannah.
Scott.
I'm Johnny.
Again, I'm Hannah, and I'm going to start by just in general looking at linear optimization. So, optimization is the process of selecting values of decision variables that minimize or maximize some quantity of interest, and it's the most important tool in prescriptive analytics. Optimization models are often used in operations and supply chain management, as well as finance and marketing, to help managers allocate resources more efficiently and achieve either lower costs or more profitable decisions. And then a linear optimization model is a model based on linear functions with continuous variables used to find a feasible solution. And a specific type of linear optimization model is an integer linear optimization model, which is just a version of the model in which some variables are constrained to being whole numbers. Linear optimization models typically have two basic properties. First is the objective function first is that the objective function and all the constraints are linear functions of decision variables. This basically means that each function is a sum of terms which are each multiplied by a decision variable. So in the example 4x plus 3y, you're adding 4 to x, which is you're multiplying 4 times x, which is your variable, and adding it to 3, which is multiplied by y. And then the second property of linear optimization is that all variables are continuous, meaning that they all can assume any real value. And we often apply this to simplify the solution method and or in analysis where the solution would not be seriously effective. However, in cases where large numbers are being modeled, such as low volume, high cost items like airplanes, rounding would have a major impact on the model. The difference between an optimum level like 10.42 planes doesn't make much sense, but if we were to round that, it would have a significant economic and production planning consequence. And then a nonlinear optimization model is a model where the objective function and or constraint functions are nonlinear functions of the decision variables, and the terms cannot be written as a constant multiplied by a variable. So an example of this would be 3x squared or 4 divided by y or 6xy. Nonlinear optimization models often require more creativity and analytical expertise and will often require different solution techniques than a linear model. Now that we know what linear optimization is, we'll look at developing a linear optimization model. All linear optimization models include the following three elements. The first is decision variables. These are the unknown values of that the model seeks to determine. And then depending on the application, decision variables might be the quantities of different products to produce, the money spent on projects, the amount to ship from a warehouse to a customer, or the amount of shelf space to devote for a project. The next element is objective function, and this is the quantity we seek to minimize or maximize. So an example of this would be wanting to maximize profit or revenue, or wanting to minimize cost or some measure of risk. And then the final element are constraints, which are limitations, requirements, or other restrictions that are imposed on any solution. And constraints can be imposed either from practical or technological considerations or by management policy. The presence of constraints, along with a large number of variables, can often make identifying an optimal solution a lot more difficult, and it'll usually require the use of more powerful software tools. And when building optimization models, you'll first need to identify these three model components and then translate the objective function and the constraints into mathematical expressions. Typically, managers can generally describe the decisions they have to make, the performance measures they use to evaluate their decisions, and the limitations and requirements they face rather easily in a plain language. And then after this point, it's the task of an analyst to take all this information and extract key elements from the basics to develop an optimization model. And then continuing on developing linear optimization models. Developing any optimization model consists of 3 basic steps. The first step is to identify the decision variables, the objective, and all appropriate constraints. The first thing we need to do is read the problem statement carefully and identify decision variables, the objective, and the constraints in plain language before attempting to develop a mathematical model. This step may seem simple, but it's really important to set up a strong foundation for the model correctly before proceeding. The second step is to write the objective and constraints as mathematical expressions to create a mathematical model for the problem. This is the most challenging part of developing optimization models. We usually represent decision variables by descriptive names, abbreviations, or subscripted letters. For mathematical foundations involving many variables, subscripted letters are often more convenient, but in spreadsheet models, descriptive names can be easier to understand. And constraints are expressed mathematically as algebraic inequalities or equations with all variables on the left side and the constraints on the right side. So the 3 different types of constraints, the first is going to be in the phrase cannot exceed, and this would translate mathematically to less than or equal to. The next phrase we see is the phrase at least, and this translates mathematically to greater than or equal to. And the final phrase we see is must contain exactly, which translates mathematically to the phrase equal to. And then all constraints must contain or must be in one of these 3 forms that I just discussed. And then the final step in developing linear optimization models is to implement the mathematical model on a spreadsheet. Here we have some examples of linear optimization models. I'm not going to go over each one specifically, but these are all, you'll notice that in each one of these, they all have an objective, which includes either minimizing or maximizing a given variable, and they all include some form of constraint or limitation. Now we're going to look at the different types of constraints. The most challenging aspect of model formulation is identifying constraints. Understanding different types of constraints can help in proper identification and modeling. Constraints generally fall into the following categories. The first is simple bounds, which constrain the value of a single variable. So an example of this would be when a problem states that no more than $10,000 may be invested in company ABC, or that we must produce at least 350 units of product Y in order to meet customer demand this month. The next type of constraint is a limitation, which usually involves the allocation of scarce resources. An example of a limitation would be problems that state the amount of material used in production cannot exceed the amount of available inventory, or minutes used in assembly cannot exceed the available labor hours. The next type of constraint is a requirement, which involves a specification of minimum levels of performance. Requirements are statements such as enough cash must be available in February to meet financial obligations, or production must be sufficient to meet promised customer orders. The fourth type of constraint is proportional relationships, which are often found in problems including mixtures or a blend of materials or strategies. A proportional relationship should be the amount invested in aggressive growth stocks cannot be more than twice the amount invested in equity income funds, or a mixture of fertilizer can or must contain exactly 30% nitrogen. And then the final constraint is a balance constraint, which states that the input has to equal the output, and it ensures that the flow of materials or money is accounted for at locations or in between time periods. Examples of balance constraints could include production in June plus any available inventory must equal June's inventory held in July. Or the total amount shipped to a distribution center from all plants must equal the amount shipped from the distribution center to all customers. Constraints in linear optimization models generally come in a combination of these constraints. In some situations, all constraints may not be explicitly stated, but are still required for the model to represent the problem accurately. Now that we know the different types of constraints, we're going to look at implementing linear optimization models on a spreadsheet. The most common way to solve optimization models on Excel spreadsheets is by using a tool called Solver. Here are some of the suggested guidelines for designing spreadsheet models for optimization problems. The first guideline is to put the objective function coefficients, constraint coefficients, and right-hand values in a logical format on the spreadsheet. At this point, you must assign the decision variables to columns and the constraint to rows, much like mathematical formula or formulation of the model. And you might input the model parameters into a matrix. If you have a lot more variables than constraints, it might make more sense to use rows for the variables and columns for the constraints. The second guideline for designing spreadsheets for linear optimization models is to define a set of cells, either rows or columns, for the values of the decision variables. In some models, it might be necessary to define a matrix to represent the decision variables. The names of the variables should be listed directly above the variable cells, and you can use shading or formatting to distinguish these cells. And then finally, the last step, you'll want to define separate cells for the objective function and each constraint function. And for this, you'll want to use descriptive labels directly above the cells as well. The optimization model that you have now developed can be used in all phases of analytics, including descriptive, predictive, and prescriptive models. We can use the model to evaluate the profit and utilization of resources in a descriptive setting to answer the question, what are we doing now? We can also use the model in a predictive setting to evaluate the forecasted cost increases or the effects of inflation in the future. And finally, we can use the model to ask ourselves, what is the best we can do with our current resources? And this way, it would be a prescriptive model. Now we're going to look at an example of implementing optimization models on spreadsheets. So this is an example from the text that looks at a spreadsheet model for a ski company. In the data portion of the spreadsheet provided, provided is the objective function coefficients, constraint coefficients, and right-handed sides of the model. This data should be kept separate from the model so that if any data is changed, the model will automatically be updated. In the model section, the number of each product to make is given in cells B14 and C14. Also included here are the calculations for constraint functions and the objective function. When we look at the spreadsheet, we're able to see the constraint functions and right-hand side values are stored in separate cells within the spreadsheet. So here on the screen, I just have the different constraints that were included in that Excel model. And it includes all individual constraints for fabrication, finishing, market mixture, and non-negativity. And in Excel, the pairwise sum of products of terms can be computed using the sum product function. The sum product function simplifies the model building process, especially when many variables are involved. So this just shows you how you're able to use the sum product function to simplify your equation in Excel. And the last topic that I'm going to touch on are some common Excel functions to avoid in linear optimization. Several common functions in Excel can cause difficulties when attempting to solve linear programs using Solver because they are discontinuous or non-smooth and they don't satisfy conditions for a linear model. Some of the functions that you want to avoid are absolute value, minimum, maximum, round, if, and count. And an example of one of these functions here is if A12 is less than 45, 0, and 1. And this would not work because the cell value jumps from 0 when the value of cell A12 is less than 45 to then 1 when the cell value of A12 is greater than 45. And this wouldn't work because in such situations, the correct solution may not be identified. And now Scott's going to talk to us about how to use Solver.
Hello, everyone. I will be discussing Solver and a generalization of how it works. Developed in 1947 by the late Dr. George Dantzig, Solver uses a mathematical algorithm called the simplex method. It characterizes feasible solutions algebraically by solving systems of linear equations. It moves systematically from one corner point to another to improve objective function until an optimal solution is found, or until the problem is deemed infeasible or unbounded. Because of the linearity of the constraints in an objective function, it is guaranteed to find an optimal solution if one exists, and usually does so quickly and efficiently. A linear optimization model, i.e. Solver, can result in 4 possible outcomes: a unique optimal solution, an alternative or multiple optimal solutions, an unbounded solution, or infeasibility. The unique optimal solution is exactly one solution exists that will result in maximum or minimum objective. As an example, for max profit, comparing selling price, production cost, cost of materials to make, and the amount of materials on hand for 3 different items, A, B, and C, a unique optimal solution would be only one answer exists for the specific amounts of A, B, and C. Say 3 dryers, 2 washers, and 4 refrigerators is the only result that maximizes profit and therefore minimizes materials and production costs while also having enough parts to build. There will be better visual examples later in the presentation. As far as alternative or multiple optimal solutions, the objective is maximized or minimized by more than one combination of decision variables, all of which have the same objective functional value. It doesn't tell you when alternative solutions exist and reports going one of the many possible alternative optimal solutions. Using the sensitivity report information to identify the existence of alternative optimal solutions. As an example, for maximum profit, comparing selling price, production costs, etc., for 3 items A, B, and C, an alternative optimal solution would be 2 or more answers exist for the specific amounts of A, B, and C. Similar to the last example, but say the results would be 3 dryers, 2 washers, and 4 refrigerators, or 2 dryers, 5 washers, and 2 refrigerators, or 4 dryers, 3 washers, and 2 refrigerators will maximize profit and minimize the materials and production costs. For an unbounded solution, the value of the objective can be increased or decreased without bound. which means to infinity for a maximum problem or negative infinity for minimum problem without violating any of the constraints. It generally indicates an incorrect model, usually when some constraint or a set of constraints have been left out. As an example, for maximum profit with the products A, B, and C, an unbounded solution would be that an infinite amount of answers exist for the specific amounts of A, B, and C. Criteria is a max profit that must be, say, X being greater than 25 and Y being greater than 10. The points of consideration are a straight line from X30, Y12 up to infinity. Since all points of consideration are greater than X25 and Y10, the solution is unbounded. And for infeasibility, it means no feasible solution exists. No solution satisfies all constraints simultaneously. When a problem is infeasible, solver reports solver could not find a feasible solution. Infeasible problems can occur in practice. For example, when a demand requirement is higher than available capacity, or when managers in different departments have conflicting requirements or limitations. As an example, for maximum profit, same criteria as in the previous example, but let's say X has to be less than 25 and Y has to be less than 10. The points of consideration are a straight line from X30, Y12 up to infinity. Since all points of consideration do not include X25 and Y10 or below, the solution is infeasible. And for solver reports, the name/report creation is solver assigns names to target cells, changing cells, and constraint cells by concatenating the text in the first text containing cells to the left of and above it. For example, if your target cell is D22 and the first cell to the left of it that contains text is profit contribution in D10, and the first cell that contains text above it is total profit in C22, the solver report will be named profit contribution total profit. And now to Lottie.
So today I'm going to show you a graphical interpretation of linear optimization using two variables. So the two variables which we are solving for are the number of Jordanelle skis that we should produce and the number of deer crest skis that should be produced. And we are representing that with the abbreviation times JORD plus $65 times DEER. The constraints of our example are in the fabrication department. There are 12 workers which work 7 hours a day, which comes to a total of 84 hours a day, which cannot be exceeded. The Jordanelle skis take 3.5 hours of fabrication, and the deer crest skis take 4 hours of fabrication, which leaves us with the fabrication constraint formula of 3.5 times Jord plus 4 times deer is less than or equal to 84 total hours. For the finishing department, there are 3 workers who work 7 hours a day, coming to 21 hours of possible labor a day, which cannot be exceeded. The Jordanelle skis take 1 hour of finishing, and the deer crest skis take 1.5 hours of finishing, which leaves us with the finishing constraint formula 1 times Jord plus 1.5 times deer is less than or equal to 21 total hours of labor. And our final constraint, the market mixture constraint, states that the number of deer crest skis must be at least twice the number of the pairs of Jordanelle skis sold, which when we put it equal to 0, we get the result of deer minus 2 times Jord is greater than or equal to 0. Another invisible constraint that here is the non-negativity constraint, which states that neither type of ski can be produced in a negative amount. So here we see a representation of that non-negativity constraint. Both of the axes start at 0 and exclude everything below it because you cannot produce less than 1 of something. So every value that fits this constraint is above the x-axis and to the right of the y-axis. And in this situation, the x-axis represents all Jordanelle and the y-axis represents the units of deer crest. This red line shows the constraints of the fabrication hours. The line shows all combinations that allow 3.5 hours per unit of Jordanelle skis and 4 hours per unit of Deercrest skis that total 84 hours. 84 is the maximum number of hours the fabrication department can allow, so all of the feasible values for the fabrication constraint are on or below this line. The green line represents the feasible values for the labor constraints of the finishing department. All points on or below this line allows for 1 hour of labor per unit of Jordanelle skis and 1.5 hours per unit of Deercrest skis. Note that all values which fit the finishing constraint also satisfy the fabrication constraint. The blue line added to the representation represents the constraints for the marketing mix. These are all values that represent scenarios in which twice as many Deercrest skis are produced than Jordanelle skis. Because this equation is greater than or equal to 0, all points above this line are feasible. The highlighted orange section shows all feasible points which are corner point of the maximums of the marketing mix constraint and the finishing constraint. The value for Jordanelle is 5.25 units, and the value for Deercrest is 10.5 units. When we plug this into our profit function, we see that our maximum possible profit is $945. The dotted lines that you see represent different values for the profit equation, equaling $600, $800, and $1,000 from bottom to top. This shows that the maximum profit of $925 is somewhere between $800 and $1,000. As Scott said earlier, there are 4 possible outcomes to a solver equation, which is a unique optimal solution, alternative or multiple optimal solutions, an unbounded solution, and infeasibility. So as we just saw, this is what a unique optimal solution looks like, because this is the only solution which provides the profit maximum. It is the unique optimal solution. Though this graph looks similar, it shows a scenario with a different set of constraints than the previous example. In this scenario, the profit line and the finishing constraint line share the same slope, resulting in many possible solutions with the same optimal result. In this situation, all points on the line segment between the 2 highlighted points yields the same optimal result of $1,000 profit. This is a representation of what unbounded solutions look like. If we go back to our original model and suppose that the fabrication and finishing departments have no labor constraints and can hire additional people as needed, in this situation, all solutions in the orange triangle satisfy the market mix constraint to infinity. This is when solver would say the objective set cell values do not converge. The text does note that there can be a finite amount of optimal solutions in this situation if the profit lines intersect the bounded region. And here we see a representation of infeasibility. Say the fabrication department requires at least 84 hours instead of less than 84 hours. Then say the points which meet that constraint, then the points that meet that constraint would be above the line and not overlap with any of the feasible regions of the marketing and finishing constraints. Therefore, this scenario is infeasible. And now I'm going to hand it over to Johnny with our team's video.
Hi. We will learn how to use Microsoft Excel Solver for linear programming-based optimization problems. Solver makes linear programming very easy. You can forget the difficult simplex methods and the graphical methods. Solver takes care of the mathematical part of linear programming. To be able to use Solver, we need to ensure that the Solver add-in has been installed. Have a look at the Data tab at the top. You should see the Solver add-in. In case you do not see it, you might have to get it installed. Now let's have a look at this problem. Maze Furniture. They make chairs and tables that have to be processed through two machines, M1 and M2. The time in hours required to make one table and one chair are given below. A table takes 7 hours on M1 and 5 hours on M2. A chair takes 4 hours on M1 and 5 hours on M2. A total of 200 hours are available on machine M1, that's the limit, that's the capacity, and 400 hours on M2. Contribution from the sale of a chair is rupees 30 and from a table is rupees 40. We need to decide the optimal mix of tables and chairs so as the maximum contribution is received. To solve this problem, we need to understand this is a classical and simple linear programming problem. The objective is clear. We need to maximize the contribution. The decision variables are number of tables and chairs to be made, and the constraints are the capacities of machine M1 and M2. So let's start. Initially, I will input the decision variables. The tables and the chairs. Next comes the contribution. It has been given to us that tables make us 40 rupees and chairs make us 30 rupees. The total contribution is equals the contribution of one table multiplied by the number of tables plus the contribution from one chair multiplied by number of chairs. In case I make 2 tables, I should earn 80, and if I make 3 chairs, I need to make 90 more, which should make it 170. Perfect. Now let's look at the constraint. My first constraint is the capacity of machine M1. Each table on M1 needs 7 hours and each chair on M1 needs 4 hours. So the total capacity used equals the time taken by one table multiplied by number of tables plus the time taken by one chair multiplied by number of chairs. Same thing for machine M2, which is 5 hours per table and 5 hours per chair. We use the same method, time for one table multiplied by number of tables plus time for one chair multiplied by number of chairs. We also need the capacity, maximum capacity of the constraints. For M1, it is 200 hours, or for M2, it is 400 hours. The formulation has been done. We can go to solver. The target cell is, of course, the total contribution, which has to be maximized. We could have minimized it. Also, the changing cells are the decision variables. I can change the number of tables and chairs, and my constraints are the capacity used in M1, which has to be lesser than the capacity available on M1. We can change this to make it equal to, greater than, make it an integer or a binary, but we'll stick to less than. We add one more constraint. We say the capacity of M2 has to be less than or equal to capacity available. We say okay. We go to options, the options button. We assume it to be a linear model, and we also assume non-negativity, that we cannot make negative tables and negative chairs. Okay, and then we leave it to solver to tell us the best solution. As for solver, we make 50 chairs and no tables, and we will have a contribution of 1500 rupees. We will completely utilize the capacity on machine M1, and we will utilize 250 out of the 400 hours available on machine M2. That's how simple it is. Thank you.
So in that video, he used a very simple example of tables and chairs to show you guys how to use the solver function in Excel. Now we'll move on to our case study, which is with NBC. So NBC is a broadcasting network that uses 4 different avenues to bring audiences to their advertisers. They have a TV network, of course, they have their TV stations, a cable network, and then they also stream on the internet. Shortly after their programming schedule begins for the year, NBC begins to sell a lot of their advertising slots for their TV channels. In about 2 to 3 weeks after announcing their programming schedule, they'll sell about 60 to 80% of their inventory. Due to this, it's very hectic, and NBC must come up with a sales plan to assist in meeting their financial goals while also helping out their advertisers. They need a system to minimize inventory assigned and also deal with their constraints. The constraints they chose for their linear plan were inventory, airtime, product conflicts, budgeting, show mix, unit mix, and client requirements. Using linear optimization helped NBC come up with a much more efficient way to develop their sales plan and to implement it. The model has actually helped them save millions, and it boosted their revenue by 50 million. It also cuts planning and all down from about 3 to 4 hours to 20 to 30 minutes. This has helped them gain a large portion of the market share, and has helped NBC stay very successful. The discussion questions that we had come up with were, in the case I spoke about how they use their linear optimization to maximize in their profits and sales goals. We wanted to know if you guys could name another use for linear optimization within a company that didn't have to do with profit, or there was the fact that they have constraints that I spoke about, such as inventory and client requirements. And we were wondering if NBC was a manufacturing company, what kind of restraints would they maybe use? We're very much so looking forward to hearing what you guys have to say to our questions. Thank you for watching our video, and we hope you guys have a great day.
Thanks, everyone.
Thank you.